Welcome back, everyone. Today we're going to play around some more with area and also start thinking about what we could do if we're staring at an area that's not just some nice geometric shape that we know how to handle. So last time we introduced some notation to help us with this. This integral, the definite integral of a function f of x from a to b. Recall this is just describing the net area bounded by the graph of our function in the x-axis, and the net word is telling us that we're counting area above the x-axis where our function is positively, and any area below the x-axis negatively, because our function is negative there. All right, and so we played around with this, got our hands on a formula, did a couple computations, got our first look at what it might look like to have some negative area where our function is negative. And then we started thinking and grabbing some more formulas as well from our handout. So we're going to continue with this and then flip over to the back side. All right, so we saw a number of different formulas, how we can get total area, how we can bound our function's integral using bounds on our function, what we get when we integrate from a number to itself. We'll zoom in just a little bit here. We also saw that integrals play nicely with constant multiples. We can pull those out and they distribute over addition or subtraction. All right, the next property I'd like to talk about is the fact that the name that we give our variable doesn't matter at all. Whether we want to call our function f of x or f of t or f of u, we're still talking about the same area. And so the integrals will be the same. All right, so for example, up here, if instead of f of x equals x, we called this function f of t equals t, sorry for the bad handwriting there, it'd still have the exact same graph and we'd be staring at the same area. The last one is a little bit of an odd-looking formula. It becomes more clear when we make all of this precise pretty soon. So normally we have our smaller limit a down below and our bigger limit b up top. If we want to, we can switch those. And if we switch our limits of integration, put our bottom up top and our top down at the bottom, it's going to give us a negative out front and give us the negation, the negative of what our original integral would have given us. So if our original integral's value was, say, 5, then if we flip our limits, we'd get negative 5. All right, so if we move over to the second page, back side of the handout, we can start putting these formulas together to find areas that we couldn't before. So let's see what we could do to compute the integral from 0 to 3 of this function right here using our previous work. And so the idea here is that we can mess with this a little bit. So for example, this denominator 2, oops, that's not what I want to do. Denominator 2, we can slide that out front of this function as a constant multiple of 1/2. And if you recall, we looked at the function x minus 1, whereas here we have minus x plus 1. Well, if we want, we can pull out a negative from both of these and flip the sign. So if we do that, this is what we get. pulled out the 1/2, and pulled out the negative, so we have minus parentheses x minus 1. Well, now using our integral properties, we can take our integral here, and it plays well with addition and subtraction. It's going to distribute to both of these terms. And this term on the left, we can have this constant multiple out front. We can take it and slide it out front of the integral. All right, so doing that gives us what we see here. Distributed the integral, pulled out the 1/2. But now, these two integrals that we're staring at, right, those are exactly the integrals that we computed last time. Right, our integral on the left, this was the quarter of the circle, and this integral on the right was the two triangles, one below the x-axis. And so if we look back at our work and fill in the values that we got there, then we can just substitute those in. So we'll get 1/2 times 9 pi over 4 minus the 1.5 value for this second integral, or 3/2. There's not too much we can do there to simplify, so here's our nice exact form for the value of this integral, and if we crank it into our calculator, it'll show us that it's about 2-ish. And if we use Desmos, we can see that indeed this is not a nice area to think about, not one that is one that we're just seeing immediately as, oh, this is like a triangle or a rectangle or a quarter or half of a circle or something like that. Now this is the graph of our function here, the function that we grabbed the area from 0 to 3. And so this is the area that we found, the 9 pi over 8 minus 3/2. Oh, and there's our 2-ish, right, that we said just a moment ago. Right, so definitely not a super clean geometric area, but using the properties that we found for integrals, we could break this apart and use our integrals for the simpler pieces to understand this area. The one thing that's kind of fun about seeing this in Desmos is if we want, we can kind of slide these sliders around. So if we don't want to go all the way up to 3, we could move that upper limit down a little bit, and we can slide that around. And as we can see, the value of the integral, right, the net area we're getting changes as we slide this around. So it looks like the integral from 0 to 1 is about 1.9-ish. All right, and we could slide that around. It's like 2.7-ish or so up to there. And we go over this way, we're getting some negative area as well. And so if we do this, we actually kind of get an idea of an interesting function we could think about, right? For each one of these choices we make for this right-hand side, we're going to get a different value for our net area. So we can actually think of this as some kind of a function where we hand it the right-hand limit, the upper limit of integration, and our function tells us, the net area so far, the net area from 0 up to that choice. All right, just these different net areas we get by choosing different values for this upper limit of integration. And for right now, this is just kind of an interesting little thought. We'll play around with it more a little bit later. But for now, let's just make a little note for ourselves that this is something we could think about. And so as a side note, if we want, we can think about our net area so far function. All right, if we want to call it g, then it's the function that we hand it our upper limit of integration, right? Our right stopping point for our area, and then it outputs, right, the net area from 0 up to that limit that we gave it, right? And here, f of x, this is just what I'm calling our function here that we've been working with. All right, let's slide on down and think about how we can actually compute net area, definite integrals, when the shape just isn't so nice. And we saw one example just a moment ago. Well, maybe we could take our function and break it apart into simpler pieces. Here's a function, root x plus 1. We don't have, 2 terms and, constant multiples to mess with and stuff like that. And so if we graph this, this is what we get. Here's the area we're looking at, right? Not a nice chunk of a circle or a rectangle or triangle or anything like that. But it still has an area. And so we'd like to be able to describe it, to get our hands on, well, what is the area of this shape here, right? The value of this definite integral. But we're students of calculus, right? And we have a motto, right? What did we do when we were estimating pi at the beginning of the semester, or when we were trying to get our hands on the slope of the tangent line, right? We said, oh, this is really hard to just get directly, but what can we do? Hey, let's approximate and take a limit, right? Get our approximation better and better and better and see what we're actually approaching in the limit, right? And this is exactly what we're going to do here with area. And for right now, we're going to start in and focus in on the approximation piece, how we might be able to do that. And so to get ourselves started, we want to be able to work with something simple, right? The whole reason we're having to kind of take a different path here is that this is a complicated shape. So we can ask ourselves, well, what's the simplest possible geometric shape that we understand area for? Right? And I think rectangles, those are great, right? With rectangles, right, once you know the length and you know the width, right, or height and width, whatever you want to call it, we know the area, right, length times width. And so let's think about how we might use rectangles to approximate our area here. And so to start off, how do you think we might just get our initial, simplest, most basic approximation with one rectangle? What might that look like on our picture? All right, well, with one rectangle, it looks like we almost have like 3 of our sides here, yeah? And so maybe just kind of complete what we're seeing in our mind. I'm using a mouse. And so bear with me as I try to draw straight lines. Oh, nice. All right, how about this, yeah? There we go. There's a rectangle. And we could actually compute its area if we wanted to, right? That's a reasonable approximation, right? It uses our area and has a little bit extra as well, but whatever, right? It's an approximation. It doesn't have to be perfect. That's what makes an approximation, right? And so here the width is 2, and the height, well, notice it's actually coming from our function over at this right endpoint at 3, right? And so the height here is actually going to be our function evaluated at 3. So root 3 plus 1, so root 4, which is 2. And so it looks like our rectangle has a width of 2, height of 2. So our area here is 2 times 2, which is 4. All right, I'll maybe record that over here. 4 is our estimate for the area with one rectangle. All right. I bet we'd like to do better, right? What might this look like, say, with 2 rectangles? Could you draw on your page what that might look like? All right, well, if we have 2 rectangles to work with, what we might want to do is kind of split this stretch from 1 to 3 in half. And if we want, we could maybe stand up a line vertically at 2, and we'll use this right endpoint that we had for our first one. And then for this stretch from 1 to 2, again, let's just come up to our function at 2. And if we come over, well, there we go. Right, now there's 2 rectangles, right? And that should do a little bit better job of approximating our function. Right, and if we wanted to, we could find the function values at 3 and at 2, and we could, figure out the areas of these 2 rectangles, which are both width 1, right, and add those up and come up with our approximation for the area. And so here we're kind of getting a sense of what our general strategy might look like. All right, and so it seems like what might be a reasonable way to go about this is to stand up a bunch of rectangles right along the x-axis, right over the stretch, the interval that we are thinking about. And for each one of these rectangles, well, we can get their height, from just going up to our function at the right endpoint of the rectangle. I like it. I think it's a good plan, and I think we should put it to work. So this was the picture for 2 boxes. Why don't you see if you can estimate that same area, but using 4 rectangles. See if you can draw the picture, the rectangles we're thinking about, and see if you can find their areas, add them up to get our full approximation. Pause the video and take a couple minutes and work that through. All right, well, let's talk about this together. So here's our basic picture. With 4 rectangles, we're not just going to cut our interval from 1 to 3 in half. We're going to cut those into half as well. All right, up to 1.5 and 2.5. And I am going to ditch just the drawing tool. I should be able to draw a line, right? Yes, perfect. Okay. All right, so we're going to have 4 rectangles. One from 2.5 to 3, right? We are, oh wow, that's really thick. Okay. You know what? I got a better idea. We're going to use the rectangle tool. How about? All right, from 3 to 2.5. Beautiful, right? And go up to the function with the right endpoint. Beautiful. It's supposed to connect right there. From 2 to 2.5, we'll get another rectangle. 1.5 to 2, we'll get another rectangle. And 1 to 1.5, we'll get another rectangle. All right? Each one of these has a width of 1/2. They have different heights, right? And those heights are going to come from the function values at 1.5, 2, 2.5, and 3. All right, so here we go. We can compute those areas and add them up. All right, so our integral here is approximately, right? So f of 1.5 times the width of 0.5 plus the function value at 2 times the width of 0.5 plus the function value at 2.5 times the width of 0.5, and then plus the function value at 3 times the width of 0.5. And if we carefully enter that into our calculator, here we actually do want the decimal approximation, since we're looking to just approximate our true area here. 3.592 is what I'm getting approximately. All right, and looking at this picture versus the picture up above, this should be doing a little bit better job of approximating our area. Should be getting closer. Now here's a question for you. This value here, is this an overestimate or an underestimate of the true net area bounded by our function? So here we can look at our rectangles. So each one of these rectangles includes all of the area bounded by our function plus a little bit extra, right? Because that's true for each one of these rectangles, this value here will be an overestimate of our true area. All right. Now, we'd like to get a better approximation, and very shortly, we'll get a better approximation by tossing in more rectangles. All right, instead of 4, how about 5, 6, 7, 8, 10, 100, etc. But right now, as we're just getting introduced to this idea, getting a feel for it, let's keep ourselves at 4 rectangles. One way that we might try and get a better approximation is, instead of getting our heights of the rectangles from our right endpoints, get them from something different. We could use left endpoints if we wanted to, but we might have a similar issue, kind of be off maybe on the other side of the true value though. But maybe if we used midpoints instead, we might have a little bit of an overestimate, a little bit of an underestimate at each case, and be getting a little bit closer to the true value. All right. So why don't you take a minute and let's see what we get. All right, so let's estimate our integral using 4 rectangles, but instead of getting our heights from the right endpoints, let's get our height from the midpoints. Pause the video, take a minute, see what we get in this case. All right, well, let's talk through this. We'll have a very similar picture to start with. All right, we have our 4 subintervals, kind of the bases of our rectangles, but now we have these midpoints that we're going to be sending up to our function to get the heights of our rectangles there. So at 1.25, 1.75, 2.25, and 2.75. So let me see if I can get our rectangles drawn in here. Maybe I'll draw them green. All right, so I'm trying to get the, oh, you know what I should do? Okay, I'm gonna start on the bottom. That'll be better. There we go. So in the function value, the height of this thing comes from the midpoint. 1.5 to 2, height comes from the midpoint. 2 to 2.5, height comes from the midpoint. And 2.5 to 3, height comes from the midpoint. Approximately in my picture. Okay, all right, so here's our 4 rectangles. And we can see that the width are still 1/2 for each of our rectangles, and we just need to send these midpoints into our function to get our heights. So doing that, here's what we get. So we get our definite integral. It's approximated by this sum, adding up the areas of these 4 rectangles, right, with our midpoints plugged into our function. And if we crank that into our calculator carefully, this is what I'm getting. 3.4-ish. And again, this should be a little bit closer to the true value than our approximation using the right endpoints from just a moment ago. All right, so this is how we can use rectangles to approximate net area. Good work today, everyone. I'll see you next time.